So this is my final lecture, and in many ways I'm going to be covering some ground that's been covered before, hopefully in a slightly different way. Hopefully it'll be interesting to you, and we'll also reinforce some of the ideas, projects, directions that we're going in this field. You as junior astronomers and junior researchers, you'll be moving up into this infrastructure that's being built at the moment, and so stand and know about it and also have input into how it develops and evolves, because you'll be the next builders once we move on and get old and retire. All right, so it wouldn't be a lecture if we didn't recap, and I think recapping is really important. So let's have a brief recap of what we've done in the last two lectures. We're generating the data that you would use to do your analysis that we would put up into the cloud or in these tools. In my case, it was semi-analytic galaxy formation models are becoming more and more common in the analysis of and interpretation of astronomical data. So we talked about this particular technique where you separate the skeleton from the flesh. The skeleton is the simulation built on an assumed cosmological model. You run one of these, you run it on one of these, a big supercomputer. The bigger the better. Actually, the more memory the better, I think, is the key way to go. You can always run it for longer with more cores. Then you attach the flesh, which is the galaxy formation model, and we played around with those in the labs. This is a schematic of one particular example, the SAGE model, which I've developed with my group. And so here's a simulation, and then we add galaxy light to that, and this is the data product that would go up to the cloud or into a database or wherever for access and analysis by astronomers who need such tools. And so we spent a lot of time talking about it's not the model or the simulation or the data itself which is important, but it's the physical consequences that it suggests. And the use of this data is key. Otherwise, there's no value there, and there's no point in putting all this data, going to all this effort to put these large volumes of data somewhere where it's accessible, and so on. And so in this case, we have the stellar mass function here, or this is actually the K-band luminosity function, and we broke the physics, the feedback physics up into two different regimes and showed how you could shape that stellar mass function by changing the efficiency of the feedback processes in those regimes. It's been emphasized a number of times, though, that the model is only as good as the questions we ask, and you have to pick the right tools for the right questions. So this is really the crux of my first two talks, and that you should never overinterpret your results. That for systems with infinite levels of complexity, there's no such thing as a correct model. Okay, it's a landscape, especially in the case of semi-analytic models. It's a landscape that you can explore the parameters of galaxy formation. And so I gave a couple of examples of how these can be used. For example, there's the void luminosity function down here. In the 2DF Galaxy Redshift survey, it was real data, and I showed how we found this new population of galaxies, not really new, but we quantified them and showed how at the brightest end, there was an equal abundance of red and blue guys. This was unusual because these are incredibly underdense regions of the universe, not really what we expected. And then we used the model to provide an understanding of how they might come about. And that was with the AGN physics, an environment-independent quenching mechanism and the halo mass function that moves relative to that. I also showed you how models maybe can give ambiguous answers. For example, we wanted to explore black hole and bulge growth, and this famous black hole bulge relation, and if we could grow black holes in a different way than the traditional way, which is through galaxy-galaxy mergers. And so this was what we get when we have a model where we grow black holes through mergers, and if we have a model where we grow black holes through disk instabilities instead, we get a different looking, but compared to the observations, basically the same answer, and this made us feel a little bit like that, right? So it was an ambiguous result, but a great use of these kinds of galaxy formation models. And what we really want are models like this up in the cloud that you can go and test these things yourself when you have a certain set of observations that you're trying to understand. So the models, of course, are parameterized, and this is really the key thing, the essential thing, right? We have to be able to modulate the efficiency of all these different processes that we think go in, so we can determine the relative importance of them under different circumstances. And let me emphasize again, the exact parameter choices are basically meaningless. Okay? It doesn't mean anything, because the questions. What is it? It's the questions we ask. So pick your questions carefully and then pick the right tools. All right, so speaking of questions, let me move on now to talking about the universe in the cloud. We've heard a lot about this already. So here's a question that I was asking probably all the way back when I was a graduate student at MPA, but certainly as I was developing my own galaxy formation models, and I was seeing the impact the Millennium simulation was having on the community as they started to use this wonderful new resource back in 2005, 2006. It was new, and it was quite all-encompassing, you know. And so I saw how people were using the simulation and galaxy formation models, and I was starting to think about these questions. So, for example, what do most astronomers actually want from mock galaxy catalogs? Right? It's a question you should have an answer to before you start building a database or a cloud service or something like that. Or at least you should have a good sense of what the answer to this might be. And how do they want to access this data? There's lots of examples in history of failed projects, because things like this one understood. Accessing data can be, you know, you send me a letter and I'll email you back a CD. That's data access, right? Of course, that's not a model that most astronomers will want to sign on to, even if the data that's there is incredibly valuable. There might be some, but most probably won't. Okay, so understanding these two questions, and this was very relevant to me at the time because, you know, Gavo was on the way. We had new galaxy formation models. We had made Redshift 0 available. And I started to get lots of emails from people, you know, I see your model online, Millennium simulation paper's just been released, this is wonderful, I want to use your model for this. And what I found was a lot of people, they don't particularly want to think too much about the model and the data themselves. What they want to do is for you to come on board their team and worry about that. And so there's a very large service component that I realized goes along with making data publicly available. And I remember as a graduate student going up to my supervisor, Simon White, and saying, you know, I really want to make my semi-analytic model publicly available. I want to put it out there like Volker Springle had done with the gadget code. I first went to Volker and canvassed this, and he said, yeah, that's a good idea. You should think about doing it. Okay, great. Go and talk to Simon. Talk to Simon, went up to Simon. Simon's like, no. You know, like, why not? He's like, well, it's not because I don't want you to make the model publicly available. I mean, that's a great thing. And MPA are pioneers in doing these kinds of things. But that he saw what happened to Volker when he made Gadget available. He became a help desk to lots of people who don't bother to read a README file, or don't understand what make really is, right? Or what a path is, or what alias means, or what export means in there, right? And it's fine, not everybody has the same level of skills, but that's what you sign on to, right, when you start making things available. So I started thinking about, you know, so what are the ways around this? How can we have our cake and eat it too? So these are the kind of conclusions that I came to. That most astronomers that I work with, at least, they don't want to learn a new language to download their data. Okay, now that does not include everybody here, right? We're all the progressives. Actually, maybe except me, because I hate SQL. But you guys are the future, right? But I work in large survey teams. I'm almost losing count of how many survey teams I work in. And my role in these teams is to bring galaxy formation models and interpretation and so on to their analysis that's being done. And this is very necessary. And I can go to extravagant lengths to make something very easy, a light cone, this and that, and give it over to the observers, and they'll say, that's awesome, great, thank you very much. Now can you do the work with that for us and write the section of that paper? All right, so they don't want to learn a new language to access that data. They kind of want it handed to them, or they want to bring someone on board. So making it as easy as possible is really key, putting it into a language, into a format that they're used to. The more you can do that, the more uptake that you'll see. If the point of you putting your data out there is to have people use it, which I'm assuming it is. And most astronomers are only interested in access. Most astronomers I know don't want to actually do the processing in the cloud. And there's lots and lots of discussion about this, about tools in the cloud and virtual laboratories and all this sort of stuff. Wouldn't it be wonderful, right? You can do your fitting, you know, on some server farm somewhere, and you can access great HPC resources and all this. It's a wonderful idea, right? But when it comes down to doing science and writing a paper, most astronomers just want the catalog. And the catalog that's cut a little larger than what they actually need, so they can trim it down, they can custom trim it later. But that's basically what they want. And again, it's a distribution power law. The number of users, the complexity, or the technical skills, or however you want to put it, right? Maybe theorists are down at the low end, but high complexity or high functionality, or that kind of stuff. Observers, I would put sort of high end, lots of them, but they don't want to have to think too much. It's an extra for their work, right? A lot of these theory tools. So they just want something that's easy to access, that's in a format that they understand, and that they can process through their own codes that they've already done their observational analysis with. Okay? So these are the sort of conclusions I came to as I was mulling this. So as a stepping stone, I kind of thought, well, here's a good way to go, right? Why don't we keep the code rather than making it publicly available, at least for now. We keep the code and we put it on our system, and we allow people to access it through a wall. And that way, no one has to install anything. No one has to use up their own resources. But they still get to run things or access the data, or something like that. And this is, of course, what Gavo did, the Millennium database that Gerard told you about. And this is what Sloan has done, essentially. So it's not anything revolutionary. But for me personally, I came to this conclusion from my own experience from working with observers and spending lots of time trying to, making data products for them, trying to get them to use it and so on, finding out what they actually like. So the work I'm going to talk about now is in large part due to Max over there, who many of you might have met as part of his PhD, and also one of my other students, Simon Mutch. And we call it the Theoretical Astrophysical Observatory, or TAO for short. And you might notice SAGE is Semi-Analytic Galaxy Evolution, so there's a bit of a Zen theme going on here. We want to be calm and centered as we do our work. We have a paper coming out, and in many ways it mirrors what's going on at MPA. I think MPA, their work with Millennium is far more advanced, far more impressive. But as I just described, the market that we're going for, really the observers and the simple side of things, where things are simple and you don't have a lot of flexibility. It's the Apple paradigm, right? You can't customize it too much, but you don't need an instruction manual either. And it does the core 80% of things that most people would want to do. So let me talk about the idea, right? And I think in this way it does vary, at least from what's going to become available to the Millennium database. So here's your data storage just there, right? And you're going to put some data in there, right? So there's a simulation cube. Could we lights off? Is that possible? All right. So yeah. So you put a simulation cube into your data store, right? As you'll actually be doing with the models that you built yesterday and over the weekend. And then what we do is we put some tools on top of that. Okay, and then we might say, oh, come in at a later date. We might say, oh, okay, there was another thing to do. Let's put that other tool in. And then what happens is that the workflow goes up through these tools from the database. Okay, and then later again, you might say, oh, that tool was pretty crap. Actually, we really need that looks like that instead. So that looks good. Okay, now we have a great set of tools and we can do some neat stuff. And so what might that be? With this simulated data cube, you might want to build a cone. Okay, great. That's what that tool does. Here, the tool does that. And then the next tool might do images, something like that. And we may want to get a little bit more build something like that. All right, so we all need a tool that looks like that. Alex, stop checking your email. All right, go totally crazy, right? We could switch out the simulation here and go totally off the scale and go crazy and build something even worse, right? Okay, so that's the point, right? And the power here is not so much in the tools, but that you can just change what's at the bottom and it will filter up through. Okay, so Millennium's great. Millennium XXL and Millennium 2 and I think that's all the Millenniums at the moment, or Millennium, right? But then there's Bolshoi, and then we have our simulations at Swinburne, Giggles, the Giggles simulations. They're the gigaparsec Wiggles energy survey simulations, or the Giggles simulations, or whatever. Someone has a new simulation and it's great, right? And how do they make that useful to the community? So all they have to do is put it in a particular format and it's in at the bottom. And then all the tools, all the hard work that went into generating tools, light cones and so on, it's all available. As long as there's a minimum set of properties there that the simulation will measure. Okay, so that's the idea. So let me just discuss Australian politics for a second. Just on a tangent here. Do people know that Australia has a female Prime Minister? She's also an atheist and single and living in sin. So I always thought that was quite amazing. That an elected leader could be like that. Anyway, it's quite science-friendly in Australia at the moment, and astronomy has been identified as one of our 3 super sciences, which basically means that the government dumps money in. And so, you know, these problems of data access and data reuse have been identified. I mean, we've been watching closely Sloan, for example, and the theory work that's been done around the world, and you know, taking note. So I was on Astronomy Australia Limited. Basically, when Astronomy needs money, right? They go to the government and say, they used to go to the government and say, we need money, and then you might get some money. Here's $100 million to do something impressive. Join a telescope consortium or something like that. Okay, that's often how it happens. And $100 million might sound like a lot, but it's how you get into these big projects and get access to 10-meter or more telescopes and so on. So the last decadal plan for Australian astronomy, they said, well, you know, we're not really very good at managing money. We're astronomers, right? We don't have to worry about that. So let's create a not-for-profit, and all the main centers in astronomy in Australia will put money into this, and they'll manage our money for us. And that's what Astronomy Australia Limited is. They're basically a not-for-profit paid for by the main astronomy centres in Australia, and they manage the money for astronomy. Not only that, they actually lobby government, and they write proposals, and they get $100 million for GMT and $200 million for the ASCAP telescope and so on. They really work hard to keep the money coming through, and then they look after that money in the accounting, the bookkeeping, and the reporting, and all that sort of stuff. So it's wonderful. And so they're connected very intimately with all the main centres because, of course, it's in our interest to have AAL, which is what we call them, be a success. And so they had a working group. They recognised that this data problem was coming. And so in 2008, 2009, a working group was formed that I chaired on high-performance computing, which quickly transitioned into e-science, data access, and so on. And one of our main recommendation was that Australia needs to build an astronomical data fabric that links data flowing from telescopes like SkyMap, ASCAP, and MWA. So SkyMap, Sloan, telescope that is Brian Schmidt's project. And if you don't know Brian Schmidt, he just won the Nobel Prize for discovering dark energy. And when you do that, again, you can get access to lots of money to do whatever you want. And for Brian, that's building his own telescope and his own Southern Hemisphere survey that will feed into, I believe, LSST and connect with a whole lot of other projects. But he basically had enough money to collect the data and do the minimum science that he had argued for, and that's all, not to keep the data or reuse it. So he was looking for a way to create a Sloan-like portal. And then, of course, there's the ASCAP radio telescope, which is the pathfinder for SKA, which will take mind-blowing amounts of data. And there's a lot of problems associated with that, all the ones we've been talking about here. And so we identified this as a key priority. This then fed into the midterm review of our decadal plan, which happened a few years ago. And one of our priorities there was investment in a national level hardware systems if we are to fully exploit the coming data tsunami. Don't you love the terminology we use? The data tsunami for the current upcoming telescopes. And if you want to know what a data tsunami looks like, this is the way. It looks very much like a normal tsunami, except it's made of data. All right? So, you know, identifying these problems. But you can see the process here. You start lobbying government. This started in 2008 to get money. Right? And so then the Australian government, so we weren't the only ones in science. The Australian government put up two initiatives as part of their stimulus to combat the global financial crisis that was going on. And they dumped $100 million. Half of that was for data storage across all science, not just astronomy. $100 million for data storage. They're going to put data petabyte centers around the country. And the other half is for what they call virtual laboratories. Okay, so you can see how the pieces start to line up. And so Astronomy Australia Limited, you know, the little poppers went off when, that here's this opportunity now that we can start to realize some of these things we've identified as priorities. All the stuff we've been talking about here. This is called NECTA, the Nationally Research Something Something Other acronym. So that was what the government created to go and decide which science projects, which science areas could get money. And AAL submitted a proposal, and this is essentially what we were proposing. Here's SCPER on this side of the country, and there's ASCAP on that side of the country. And we wanted to link them. We wanted to do this data federation, okay, so that the astronomer sitting in the middle didn't have to smash his screen, that he or she had access to this amazing optical data and this amazing radio data and could cross-correlate them and do all the wonderful science that they want to do. So multi-wavelength Sloan database, basically, where it all comes together. And so we were successful, and we had one of the largest proposals. And so I think it's still kind of small compared to what stuff that Alex is doing, but it's brand new in Australia at least. The proposal was the All-Sky Virtual Observatory. Because of the nature of the funding agency needed results on a 2-year timescale. ASCAP won't really have any significant data on that timescale. They will, but not enough to fill a data store. So we had to drop ASCAP off the list at least now, which is very convenient for me because I'm a theorist and I have simulations. So I said, well, I have an idea that we can add to SkyMapper. So for the initial realization, we have simulation model data and optical data. Okay. And this project just started in June. We're in the process of hiring software engineers and dealing with all these weird things that I have no idea about, like milestones and stuff like that, reporting and all this project management type stuff. But it's a real project that's going ahead. So one of the reasons why I was able to argue for this is that with Max we had been building a prototype, modeled in many ways in spirit on my experience with working with observers and building models for teams and so on, and also, you know, my time at MPA and watching what they've been doing there. So here was the idea that we argued. This is what we wanted to produce, or what we are producing. As I showed you before, you know, a simulation database at the bottom level. We wanted a web form data query. Okay, so we do have SQL in there. Okay, but as I said right up front, in my experience is most observers don't want to have to think too hard to get their theory data, and they certainly don't want to, especially if they have a complex query, they don't want to be, you know, struggling with errors and this and that. They just want to press a button, a couple of buttons, and get something that's pretty close. Then they can filter it through their own codes. So we've decided to go with a web form query, and I'll show you that in a minute. Then on top of that, spectral energy distributions and filters. Okay, so this is a module. This is not something. So the original galaxy formation models on Millennium, they were run with filters. So part of the output, including, you know, like stellar mass and star formation rate, was BVRIK or UGRIZ filters. Okay, so separate that out because your needs might change. You might want radio, or you might want X-ray, you might want infrared, or something like that. You might want the entire SED. Okay, so we want to do that as a module in post-processing. Not only that, but there are different models for how you should build that SED, depending on the star formation history and metal history of each galaxy. And you might not like the model that we initially chose. If you don't like Bourgeois and Charlot, it's too bad. Millennium, at least, with the original models, that's what you get. Okay? And there are ways around that, but it requires some work. Put that as a module step. Once you have SEDs, you have luminosities, apparent, then you can get apparent magnitudes for galaxies, which means you can put them on the light cone. From that, you can get image generation, and combining all this together, you can mock up a telescope simulator. And so this is basically what was in the proposal to fund through to 2013 to build. And a lot of this is very, you know, is what's been happening at Munich as well, which is great. All right, so this is where we're at. I'll show you this in a minute. I'll show you our prototype. We have Millennium, Bolshoi, the Skiggle simulation. In terms of the simulations that go in, we have the SAGE model and Andrew Benson's Galacticus model for people who know that. And we're looking for others at the moment. It's a matter of coming up with an agreed data format. But again, you can switch out the simulations and the models however you want. It doesn't change what comes above. Simple, no SQL, although you can flip things around and put in SQL queries if you like. We're almost finished doing our SEDs. This is an insanely difficult problem, it turns out, to do in real time or pseudo real time. It's not so hard for a few thousand galaxies or even for a few thousand galaxies, but when you have tens of millions of galaxies, building SEDs in a time that you know, that's useful for you to access is challenging. So light cones are something everybody's building now, so it's not too difficult to make. Image generation will use the output from the SEDs and the light cones and then the telescope simulator, okay? So here are emoticons to describe our progress. All right, so this is what it looks like. Let me flip over in a second, or let me flip over now to show you what our prototype looks like. And this is live. It says beta here. It's interesting to see the different cultures, because in software engineering space, they kind of scoffed at this idea that this was a beta. Right? They called it a prototype. Right? So you don't make betas are for things that actually work properly. This is a prototype to demonstrate a concept. Touché. All right, so it's pretty straightforward. It's about as straightforward as you can get, and that was the goal, to make it Apple-like. And we're going for Apple-like, not Linux-like here. So we're going to limit what you can do. Okay. Hopefully you can just download that, what you get out, and then do the extra stuff you want. So let me come back to catalog type in a minute. Is this displaying? Yeah. All right. So for what's online at the moment, we just have two simulations. But notice the bar on the side, the information on the side, as I change the simulation. And so we'll have Bolshoi and we'll have others in there, and all this stuff will auto-update with information. So again, two galaxy formation models in here, and things update in real time. So what we basically want to do is have every combination of simulation and model. And then the stellar model, this is kind of limited at the moment. We're going to expand this functionality once we get the full SED stuff happening. But if you like Mariston, then pick that. If you like Bruswell and Charlot, pick that. Everything else will be the same. Okay, and then you can decide how you want to cut it. So at the moment, you can only cut on one property. Again, we're just limiting functionality. So you can't do a select star from B minus V of blah and halo mass of blah and all this. Okay? If you want to do a particular thing, then you just say, give me all the galaxies with galaxy masses greater than this, or halo masses in this range, or something like that. Very simple. You're going to get a data product back which is large you need, but you can cut it down later. And in my experience, I found that's what most people want anyway. They don't really know exactly what they want when they go and get their data. It's only when they start analyzing it. And so then you can set the limits, pick your redshift. All right, so let's do Sloan, and box size here. So this is the millimillennium. We can change that to 500 megaparsec cube or whatever. Now output properties, of course, you can now select what you want in terms of the information you get back, and you might decide, we have absolute magnitudes here for this particular one. You might just decide you want everything. Okay, pick your format. If you're a theorist, you might want HDF5. If you're an observer, you might want FITS. If you're really, really old, you might want ASCII. Okay, I hope we at least zip it. Yeah, we do. Could be traditional and not zip it. Just let them download it for the next 40 hours on their old 56K modem connection. All right, and then you put in your email address. Okay, put your email address in and then hit submit. Okay, and you'll get an email, which I'll show you in a minute, that says you've submitted a request for data matching this. Okay, and because this is very simple and there's nothing else to do here but query the database, much instantly you'll get an email back saying, oh, we've got your data for you. Here's a link. Click on the link, you'll get your data. Grab it in 3 days, otherwise we'll delete it off our system because we can't just accumulate everybody's unwanted catalogs. Okay, so pretty simple, right? Kind of as simple as you can get. Click some buttons. So where the power comes in is now doing extra things. And so we've got light cones going. So watch, when I change the light cone, things change. Okay, so now in addition to the stellar model, there might be survey presets. So a 2DF type light cone. Maybe we want it on Bolshoi. Oh, we lost a lot of options there. We're still implementing a lot of this stuff. The full millennium. We want unique cones. So I believe both Risa and Harad might have discussed building cones that you have to cut through the box to build your light cone. And you take the box at earlier and earlier time steps as you look back in time. And what you end up doing is cutting across structure that you've already included at earlier times, well, at a closer distance, because the box has a finite volume and the light cone can go on for a long time. But you might not want that. You might want a light cone that's actually unique, where you don't replicate any structure, and that limits the number of cones you can get back from a given simulation, but that might be fine. And so, you know, our algorithm can work out how many unique cones you can get for a given choice and so on. Or you might just want random, you know, a random cone. And you can specify how many cones you want back. So if you want 10 Sloan cones back from Millennium XXL, if we put it in here, then you can do that. And it'll randomly pick the observer and then cut the cones out the way you ask. All right, and then again you can filter, but now you can filter on, we don't have apparent magnitude filtering in here yet. We're still working on that. Brightest and faintest, redshift range, RA depth, so you're picking the area on the sky. All right, so it's build your own cone, so you don't have to go and write any code to do this now. And again, don't like the simulation, pull it out and use a different one. Don't like the model, pull it out, use a different one. As long as we get these simulations and models in an agreed format, We can put anything in there as long as it has a minimum amount of information that the modules need to process. Pick your property. We're going to be progressive here and get HDF5. Put your email address in. Now that gets batched off to the supercomputer at Swinburne. It will build your cone, do the queries, do the SED stuff, put it all together, and depending on how complex it is, it might take a few hours. Cones still take some time to do. Of course, we're going to try and bring that time down as best we can. But that's fine. You're going to get lots of cones back, and then you'll get an email saying it's done. Okay, and so you can see how we can add functionality onto this by putting image generation, and we might have some kind of UML flowchart diagram as well to process, so you can take the output of one thing and feed it into another. All right, so that's in essence, what we've done, what Max has been building, and it's sort of the anti-Garvo. It's the very simple version. There's a lot of things you can't do. It reduces your options, but you don't have to think too hard about what kinds of catalogs you want. And so we're not going for the power user here. The power user, we may have other tools they can use, SQL boxes and so on in advanced tabs. But generally speaking, we're not going for those people. We're going for the observer who just wants a quick catalog to compare to their observational data. Or they want, if there's a professor and there's a student whose project is mostly observational, but they want to do some theory comparison between a couple of different models or something like that, they can easily go here. They don't have to spend weeks working out how to get a catalog, or maybe hours or days working out how to get a catalog, but then writing some software to build a light cone on that, and so on and so forth. We're hoping to make it really easy for people. There was one other thing I wanted to say about that. Yeah. So the other thing it does is it helps with these these analyses that we're just starting to do, which is what we should be using these cloud services for, is to say, here are a set of observations I'm trying to understand. So as we've been working in our labs, here are these observations. Here are 3 models, and I don't really know how these models work because I didn't do them, and it's all a bit hand wavy to me. However, these are popular and are well quoted in the literature. So I'm just going to take these 3 models and I'm going to do the same analysis on 3 to get a sense of what the theoretical uncertainty is. Okay, so that's a good use of the models, just to get a sense of the theoretical uncertainty. And the nice thing is they're all going to come to you in exactly the same way. Or I'm going to take one model and I'm going to get the results back on 3 different simulations. So what happens when mass resolution, when I have a simulation where the mass resolution is really bad, like Millennium XXL, not that great mass resolution. Very big, but not that great. So does that have an effect on the conclusions? Is the science I draw from this model sensitive to these things? And so now you can get identical results and out the models and simulations. And so that was one of the goals of this, to make it a common interface where you can draw this sort of stuff from. All right. So the 3 simulations we're focusing on are Millennium, Bolshoi, and Giggles. And as we all know, simulations come in different colors. So red, green, blue. And different models. This is a schematic, a sort of more generalized schematic, but we worked with one particular model, but there's nothing to say that model is actually a better implementation of galaxy formation physics than another model. These ideas have to be tested, and they all have strengths and weaknesses. So we're working with other groups to incorporate other models in here. This is an example of the email you get. Your job was successfully submitted with some information, and when it's completed, you get an email back saying, "Congratulations! Here's your download link." Okay. So this is just an example of a light cone that this builds, and we use the standard techniques now of rotating and doing mirror imaging to avoid the replication of structure, at least the visual replication. And there's lots of checks that go on in our code and in our analysis to make sure that we're not breaking the correlation function, for example, on larger scales and so on, that the overall distribution of galaxies doesn't change. And here's just one example of something you could do really quickly. So for the candle survey, we just built a light cone which mimics survey. And the first question we asked was along this light cone in a limited redshift range, so around redshift 4. Let's just plot all the galaxies in that light cone with stellar masses greater than 10 to the 9 solar masses. So that's the top bar there. And then let's impose the I-band magnitude limit of 28 points. And so this is the limitation candles will have to deal with. This is what the data that will get back. Again, sticking to galaxies greater than 10 to the 9 solar masses. Okay? And now we can look at galaxies fainter than the magnitude limit in this mass range. And it's not as obvious. You can see the little smattering of blue dots down the bottom. So these are all galaxies that candles will miss. And depending on your particular science questions, these galaxies might actually be very important. And so you want a sense of what the survey may miss and whether this biases your analysis or not. And it's very simple to do with these kinds of web interfaces. You click a few buttons and select a few drop-down boxes, put your email address in, and you'll get something back that you can analyze. Now, this will be, this result is based on one particular model. So again, you want to do this for a couple of models, and that's the idea of having drop-down boxes where you can just switch out your model. It may also depend on the simulation. You can do that again. The other nice thing is that we want to do is there are a lot of people now running alternative gravity, alternative dark energy models. And so we can run the galaxy formation models on these and look for differences as well. So having a repository where there is lots and lots of different simulations, different kinds of simulations and models, I think is very valuable. So here's another interesting thing. This doesn't have a paper associated with it. It's just something interesting that I found. So just go and give me all the things with high star formation rates, galaxies with star formation rates greater than 100 solar masses at this redshift. And if you plot that by halo mass, it's bimodal. Right? I wasn't expecting that. So just really simple query, and actually figured out why it's bimodal. If I output also the morphologies of these galaxies, it turns out that this lower plume, so this is halo mass and star formation rate, this lower plume here basically merges. This is bulge to total now just for all these points. So these are mergers, so these are star bursting guys. That's why their star formation rates are high. And these ones in the higher mass halos are essentially just massive disks at these high redshifts. Right. So I probably would have never have noticed this, but it's a really easy way just to get at information like that. All right, so what do you get? You get multiple simulations and multiple galaxy formation models and preset survey parameters. The other thing we're hoping to do is we want this all to be not necessarily open source, but open to the community in the sense that if you run a new simulation or a new model, as long as we have an agreed format, you can send us that data and we'll put it in and people can access it. And I go to a lot of conferences and it's a bit like we're all like traveling salesmen now, right? We're selling our latest model and our latest simulation. Here it's online and here's the link and go download it and use this data and it's wonderful, right? You can do science. And so why do we do that? Partly because we're generous, because we like the attention, I think. We're also collecting citations, right? That more people who use your data will have to cite it. And that means that you can do more in the future when you go back and argue for money to do new projects or put in a new HST proposal or something like that. Okay, so it's kind of good for everyone. So that's why we do it. It's not necessarily a selfish thing. So if you run a new simulation, you don't want to have to go back to square one and then create all the infrastructure to build light cones and put it online somewhere and so on. And so we want to provide sort of a back end, sort of a framework for people to do that. It also comes to the issue of data access. So I know with observational data, HST, for example, there's a proprietary period and then you have to make it public. With theory data, I don't believe there's any equivalent requirement. Do you know about this? If you run a simulation on a national resource here, do you have to release the data in a certain period of time or is it yours forever? It's yours forever.
The National Science Foundation now requires a grantee to describe their data sharing plan. But it hasn't been
Yeah.
implement.
And for good reasons, because how do you do that? And no one's going to pay you to hire someone to go and put this in the right form, write the documentation, and it's difficult to do and costs money.
Yeah, so the NSF says, you know, you should do this, but only at incremental cost.
Yeah.
So what does that mean if you're generating 200 terabytes like me?
Yeah. You do it at, like, you know, in megabyte increments. Yeah, and so we have the same thing in Australia with our national resources and time allocation committees. They're saying, well, if you're going to use taxpayers' money to run these simulations, you really should release it to the community after a period of time. And say, I would love to do that, but, you know, other than putting a, you know, gigabyte tar, you know, X gigabytes tar on a link, you know, linked somewhere from my homepage, how am I going to do that? And so the idea here is to provide a way for people to do that then they can make their data public for their own benefit, but also to satisfy these requirements. And this is the future. Get used to it. When you use taxpayers' money to do something significant, you're going to have to make it available to the public at some point. All right? So just get used to it. But the benefit of that is when other people do the same thing, they'll have to make it public, and so then you can use it as well. And hopefully we'll all get good at documentation, and this whole field of astroinformatics will expand to easy to do and convenient and not inconvenient and difficult. So we're working on light cones is pretty much solved. Telescope simulation is a little bit ambiguous of exactly what that means, but we'll come up with some definition that will work. SED modeling is really hard to do on the fly for so many galaxies, and we have a GPU supercomputer at Swinburne, and we're probably going to have to use a lot of that and think really hard about how that happens. What's hard about it is that to get the apparent magnitude of a galaxy along the light cone, you have to know its star formation history up to that point in time. Now the model has star formation histories. You are outputting star formation histories. Actually, I don't think you could have output star formation histories if you wanted. The tricky thing is that the simulations are all on fixed time grids, but to build an SED you need a finer time resolution closer to the point that you're observing the galaxy for the bluer parts of the spectrum. So if you want blue or UV or something, your time resolution for your star formation history needs to be, you know, 1 million years, 5 million years. The time resolution of millennium is between 250 and 350 million years. Right? So how do you get a UV or even a B band, an accurate B band part of the SED to put filters on top? And so it becomes very tricky. There's a lot of interpolation. And then you have to do it at any arbitrary point along the history of the galaxy. So you can put that galaxy on the light cone in an accurate way that when someone downloads it, basically using a black box, it's meaningful and it's not wrong. Okay? So it's a really tricky problem. Then you have to do this for tens of millions of galaxies, potentially, in real time. All right, so it's a challenging problem, but one that we're solving. Real-time mock image generation, I mean, I was insanely impressed by what Gerard was showing. I mean, just amazing. So we're not going to be able to compete with that, but we'll be able to, for an arbitrary SED and light cone, we'll be able to give you images back that you can then do your own analysis on, so we won't provide analysis tools like Gerard is doing. And then we're working on some other things like resolved disks and bulges and so on. All right, and so the natural extension for this, and actually is where this all started for me when I sat down in Simon White's office and said, I want to make my model publicly available, is actually doing modeling in the cloud. So, you know, you're not just bringing down somebody else's model, you can make your own. Now, there's some problems with this, which you only really realize when you start to try and do it, but I'll just show you our little Tau labs here. So firstly, we have Galacticus. So this is Andrew Benson's publicly available model. And basically, this is essentially just a web form for his input file. And so you fill in all these parameters. We can improve this. We've talked about improving this and simplifying it. But these are all the different parameters and choices you have to make. And then the different outputs that you might like to get. Again, put your email address in here. And what it does is it creates an input file, creates the executable, batches it off to our supercomputer, runs it, brings it back to the server with a link, and then you can download the result. Run this in the cloud, and you don't have to install anything on your home machine. So this is a wonderful idea in principle, but hopefully, as you all found over the last few days, that you don't just want to run a model once. If you only want to run it once, then it's easy. You just download the default model that people are offering. If you want to explore parameter space, you're not going to run it. You're going to run it many, many, many times as you explore. And you don't want to be sitting clicking boxes on a web form and hitting submit and destroying our server, especially across the Pacific. So we need to think up a better way to do this. Okay, so in principle, this is a good idea. You can run your own models. Wonderful. Let's give you that power. No one can complain that we fixed everything. But in practice, we need to think about how we do this. And one way might be to have online MCMC tools. So instead of running the model by picking the parameter choices, you might specify a range. Or maybe there's a range already specified, and then you upload some observations that you're actually trying to match. And some MCMC tool will go and tune that model for you, given the observations that you've decided are the most important. And then that will return those parameters in the model back to you, maybe the likelihood contours for those parameters, and so on. Perhaps, maybe that's the way to go. And if you're interested in dwarf ellipticals on a particular simulation, then you can do that. If you're interested in BCG evolution on another simulation, you can do that. Those models might act different, but you just want to calibrate a model for that data so you can use it. That might be the way to go. So the other thing we've been exploring is what we call PySage. And essentially this is a wrapper to the Sage code that you've been using, where the different physics modules now are not written in C, but they're written in what we call pseudo-C. So you have this technical problem. So for those who are coders, hopefully you'll follow this, that you have a list of properties for a galaxy, and you have to define those properties in a header file somewhere, those structures. A galaxy has a disk radius and a stellar mass and a hot gas component and a cold gas component and all this sort of stuff. This is what you're running. Now let's say you have new physics in a module that has a new component, let's say the intracluster stars, and that's not in your model. In order to put that into the code, you not only have to put a module in that describes the physics of how intracluster stars fit into the schematic. So when do you add these stars to this component, all that? That's the module that works with the physics. But you have to go and update the structures at the start of the code with the header files. You have to update the output file, all this kind of stuff. And so it's all, you have to go through the whole code basically and initialize these new properties and so on. So it's not as easy as just slotting in some new code that describes that physics. You have to change many, many parts of the code, and that becomes problematic. So the way around this is with PySage, where each module is in sort of a pseudo-C now, where you define the properties that are needed for that bit of physics at the top, and there's a Python wrapper, and it strips off all this information and goes and recreates the structures for you, put file initialization and all that on the fly when you actually compile it. Right? So it rebuilds the code every time based on what you've specified. Now, is that in theory you could have this online and you could upload modules, and as long as we tell you, what to put, or it could even be a form-like thing where you put all the properties that are needed, as long as the wrapper knows what they are, then it can build these structures for you when it goes and compiles the code. And then in theory, this could be like a UML diagram, a flowchart type thing where you take, hot gas to cold gas, just like I was drawing on the board. You could build it that way, build up a model that way, and the code generation happens behind the scenes. Then you pick the simulation you want to run on it and the properties you actually want to output. So I think this is the future in the next 5 years. It's easy to describe, but really, really difficult to actually do in practice. So it's very challenging. But I think this is where we're moving. And then you can run your own models. And then you can imagine if we solve an MCMC calibration, the calibration challenge, you could couple these things, these different tools together. So this is where we'd love to go. What's essential, I think, is that we need to decide on some common data format. And Gerard talked about this with the IVO standards. And not only that, but we need to be able to share codes, simulations, and models. And when I say codes, I mean, for for example, no one should ever write a light, code to generate a light cone ever again. It's a solved problem. It's been done so many times. It should be a library function somewhere. Okay, for example. But in order to do this, we need to start finding some common ground with the data structures we use and talk to each other. All right, so let me wrap up. I think we should be aiming for simple access. If we reach the maximum number of people, we'll always have a power user, say we have to cater to them. But I think the majority of science with this kind of stuff will come through. The simpler the better, really. This is just in my opinion. And ideally visual. This visually without coding, great. And even better, if it could work on an iPad, we could do it on the train while we're going to work or something. Wonderful. We need common data changeable tools. There's no reason why I shouldn't email some code to Peter or to anyone. This generates images, and it just slots into the existing code you have. Same model on different simulations, different model on same simulation. Lots of science applications there. And then ultimately some online natural language analytic and semi-analytic modeling, enabling people. So the idea of writing code to build semi-analytic models becomes something in the past. The code is all written by some parser scripts, whatever, that happen in the background on a supercomputer, and you basically describe the galaxy formation model, and all that technical stuff is done in the background. And the most important thing here is transparency. Okay, we all need to understand what's actually happening, what the corners are, what the assumptions, and so on. And as you've seen, hopefully, it's about the questions and the science. All right. I went to a workshop on surveys a few weeks ago, and there was a very nice thing. Matthew Collis. So people who don't know Matthew Collis, he was the PI of the 2DF Galaxy Redshift Survey. He's the director of one of the national optical facilities in Australia. And he said, prediction for astronomy in 2022, data scientists will outnumber observers 2-to-1. Who thinks that will happen? Data scientists.
In all fields or in astronomy?
In astronomy. Probably true in all fields.
Wait, when?
2022. 10 years. No. Right. We should put money on this. I think it will. I think it's already happening. Yeah, maybe. But it's going to become increasingly important. Yes. So if you want a job.
Yes.
Okay. So everybody should be writing that down. All right, so I started by saying these were the 3 topics I was going to cover in my lectures: building synthetic universes, parameters of galaxy formation, how do you use them, what can you do with them, and then the universe in the cloud. So I hope I've touched on topics in sufficient detail to sort of answer my goals that I said in the first lecture, which was that I wanted away with having a basic understanding how these galaxy formation models are constructed, how general, broad understanding of how galaxy evolution proceeds, so that when you see someone present some results, you have at least some depth of knowledge of what went into producing and what, where you should be skeptical and where you should be impressed, basically. And these uses and limitations are really, really important. And I've talked about the challenge of data access and delivery, and I guess more the vision of where we would like to go, although it's a long road, and things that sound simpler are insanely difficult to do. So I'll end there with these links. Feel free to go and use our mock galaxy tower. As I said, it's only a prototype. It's just a small Linux box on Max's desk, and so I think, somebody said they literally set their computers on fire. You might actually start a fire at Swinburne if you're going to access it. But it's there to use. It's in the early stages of development. It's nowhere near as advanced as the stuff going on at Munich, but we're learning every day, and professionals now who can help us to turn this into a real product that will be useful to the community. And if you want to know more about the All Sky Virtual Observatory, which this project we've just started, then you can Dan, and I think my time's up, so thank you very much. Yeah.
So how scalable is the infrastructure behind this? Like if it's suddenly your whole system catches on and everybody starts using it,
Yeah.
How can we go down for 6 months?
You know, ideally, I'd love to have it in Git, and then you just check out a new copy of it somewhere else in the world. I mean, I'd love to have it set up, you know, different portals in different continents with mirrors of the databases and so on. So, so we had dinner last night, and we were talking about how you make these things happen, right? Because they sound, you can describe them in such simple terms, and then when you go to do them, you don't appreciate how difficult they are, the challenges are sometimes, and it's only after a lot of effort that nobody sees they work. And so, you know, what causes one project to fail and one to succeed? And, you know, the answer, I think, is that you have to start with the absolute simplest thing and get that working well, which is kind of why we've taken this approach. I mean, our endpoint might be the simplest thing, and I'd be happy with that. As long as it does exactly what we sort of envisage, I'd be happy and let others in the field lead in the more advanced tools. We'd be fine with that. And if we achieve that, then it's going to be, you know, by construction, simple to move around then as well. And then we can have mirrors in different places in the world, or people may even be able to set up their own private server for a team or a consortium, whatever, a group of theorists, whatever. So, but that's the goal. Yeah. Yep.
So it's really cool that you can get this online, but supercomputing time is very expensive. And so after your funding runs out in 2030, how do you pay for this going? How do you pay for this in the long term? Otherwise, it's just kind of a pet project for a couple of years.
Yeah. Well, one thing you realize is that everything is a short-term project in terms of funding. So, you know, most telescope projects only have funding to build the next thing, and they have no idea how they're going to do all the other stuff after that has to happen in order to make a real telescope. And if you worried about all that and didn't proceed until that was a certainty, then you wouldn't do anything. We have funding. So this is, of course, written into the agreements. So you know, there are teams of lawyers that sign stuff with governments to make this project happen. And one of the things is we have to maintain it through to the end of 2014. And we have funding for that. So we have funding to build it through to the end of 2013 with different stages of development. So it'll actually go live and online by the end of this year in the initial stages. And funding to support it through to the end of 2014. So that's quite a long way away. And if it turns out to be useful, if people are doing science with it, it's not going to be hard to get funding to continue to support it. And one of the things you do with projects like this is you use them as leverage to build new infrastructure. So not just the infrastructure for the project, but teams of expertise that can do the next generation or the next level for this project or new projects or whatever. So one of the ways we're looking at this is that we want to build up a team of software engineers at Swinburne that then go and build new things. And if this is a success, we'll be able to do that. And then continuing support and funding for this won't be a problem at all. Any more? Okay, let's break. Thank you.